Welcome to Quality Improvement Lecture 2. This is for our Stat 435 students at Virginia Commonwealth University, but anybody can use it. All right, so this is Lecture 2, and the first lecture we talked about the basic definition of what quality is, and here's the definition is quality is fitness for use. A quality item is one that you can use, and it's already ready to be used. You don't have to, use a shoe to put a nail in a wall. That is not quality. But a hammer is a much more quality item to do what you need to do. Okay, the modern definition is quality is inversely proportional to variance. So if you'll see what I mean in terms of variance, and if lots of the items are different from each other a lot, then they're not interchangeable, and so they're not consistent. So that's variation. When things are not consistent, it's variance. And when you think of a high quality item, you think of it being very precision, not a lot of variation in it. Okay, parameters are often called quality characteristics or critical to quality characteristics. Okay, so this is the thing that you really care about, okay? These are the things that you're going to measure because they matter. They matter to you, such as physical things like length, weight, voltage, viscosity. Things like that are important to know, and you want to make sure that they, if you have a part that needs to fit between two other parts, the length probably matters, because if it's too long, it won't fit. And if it's too short, it may not do the appropriate job. It may not be fit for use. Could be sensory. Taste, appearance, color. Think about if you're making coffee. The taste can be vary widely on different types of coffee depending on how they roast it. Some coffee tastes burnt, some does not. Some people like it more bitter, some people like it less bitter. So all of those matter because you want it to be consistent, so that when I go to my favorite coffee place and I get some coffee, I would like it to know what it's going to be before I taste it. Okay, that's what we mean by quality. There's not a lot of variation every time I get a new cup of coffee. Could be time orientation, such as reliability, durability, serviceability. Does it last a long time? That's the durability. Reliability means every time I use it, do I get the same thing? And serviceability means if it needs fixed, how are you able to fix it? So whatever these the customer's going to define these critical to quality characteristics, not you. Okay. So they're going to set some specifications. So there's going to be what's called the nominal or target value. So this is the desired value for the quality characteristic. So if they tell you that your tire pressure is supposed to be 35 pounds PSI, well, that's what the target is. But knowing that, it's hard to hit exactly 35 pounds of pressure, there's an upper specification. It's like, don't go any higher than this, because if you go higher than this, the tire might explode. But it also has a lower bound as well, because if the pressure is too low, then the tire may wear poorly, or it might break as well, because there's just not enough pressure in it to actually do its function. So keep that in mind, that specifications are going to be important. All right. So we've been talking about this idea of quality and quality control and improvement. And it has really three major areas. There's what's called statistical process control, or SPC. And in this, we're going to be interested in monitoring a process that we have control over. Notice it has the word control in it. The second one is design of experiments. We would like to design an experiment to find out where sources of variation are in our process. And then there's acceptance sampling, which is, well, if I get a new box of parts or items shipped in, how many of them are good? Are they good, or should I send them back? Okay, so we'll talk about these briefly. First thing is, what is a process? Okay, so basically what you're going to do is you're going to have some inputs Okay, these are raw materials, components, subassemblies, or it could be even information, okay, that you're going to put into the process. That this is what the process is going to act upon. Then you have some of these, what are called controllable inputs. So, and I'll give an example of it here in a minute, but you have control over these versus down here, you're going to have uncontrollable inputs. You don't have control over these, and these will also cause variation in your process. You're hoping that the variation that is caused by these controllable inputs, you actually control. Okay, once the process is done, it's going to put out a part, and we're going to call Y the quality characteristic, or the CTQs. Okay, then what we're going to do is we're going to take that output, and we're going to look, and we're going to measure it. We're going to evaluate it. We're going to monitor it and control it. And that's how we're going to do that is by adjusting these controllable inputs to make sure that our quality characteristics make the output what the customer desires. Okay? All right. So what is the process? Take inputs such as raw components information. We're going to have controllable inputs. These are process variables. Uncontrollable inputs, Z, have influence. This produces a product, Y, with our quality characteristics. We're going to measure, evaluate, monitor these, and adjust the controllable inputs as necessary. Here's a simple example. Nobody makes bread anymore, but bread to make is actually quite an art. It only requires 4 ingredients. Okay, so these would be our raw materials. We're going to need water. We're going to need flour. We're going to need some salt, and we're going to need some yeast. Okay, and I can take these, and I'm going to put them through a process that will ultimately turn it into a loaf of bread. Okay, so the process together, we have the following controllable inputs. That means we can actually control these. So, like, for example, the temperature of the water. If the water's too warm, it can kill the yeast. If the water's too cold, the yeast doesn't activate as quickly. So that's one of the inputs. Ratio of flour to water. If I have a bread that doesn't have a lot of water in it, then the bread is going to be far denser than one that has more water in it. Okay? The amount of salt. The amount of salt will influence the bread because the salt provides taste, but salt will also kill yeast. So you want to put it enough that it tastes good, but not too much to kill the yeast in the bread. Okay. Another input is how long did I leave the bread to rise? Okay. You read a lot of recipes says wait an hour or till it doubles. Okay. Other people say, oh, well, there's this overnight bread where you let it rise overnight. How many times the bread is needed? Sometimes say, you knead it and then you stop and then you just let it rise and then you do a little bit of kneading and then put it in the oven. Other ones say you should knead it like every half an hour. The temperature of the dough as it rises. Some people say you should put it in an oven or basically a proofing box that keeps the temperature consistent, and you control that temperature. The temperature of the oven as the bread is baked in, that's obvious, right? You're going to put it in an oven, you have to set a temperature. You have control over that. And how long the bread is in the oven. You have control of that as well. Okay? You have other things that you can't control. Okay, so some uncontrollable inputs is the age of the wheat before it was ground into flour. Was it just harvested, dried, and immediately turned into flour, or had it set in a silo for a year before it was ground into flour? Maybe that affects it. The humidity of the ambient air around, because there's a ratio here of water to flour. Well, if the air is very humid, that flour might be picking up extra water from the air. And the consistency of your oven temperature. Some ovens are very consistent. And they can keep the temperature within a few degrees of the target. And other ones, they let it drop maybe 10, 15 degrees, and then the element kicks on, and then it raises it up, 10 or 15 degrees above the target so that it cools back down. And on average, the temperature is the same. You don't really have control over that. All right, so those are what a process is. And then the next of these is, I need to see if my process is behaving. Okay? What we mean by behaving is it turning out consistent parts or consistent products or consistent information. So what you would do is use a control chart. And this is an example of one. And basically, you're going to plot the averages of measurements of your critical quality samples from the process over time. So this dot here is at a specific time. That would be at time 1. This is the point of the average. Okay? That means there were multiple measurements taken in order to make this average. At time 2, you took another sample. Maybe you took 5 or 6 items, and you calculated their average. And on average, you can see how the averages move around. Okay, that's what you're trying to look at. Okay, the CL is the center line. Okay, and it's the nominal value. What you would like the value of the mean of all the parts to be, or what you would like the part to actually measure if you could measure it that accurately and produce it that accurately. That's really hard to do, to get it dead on, but you can't get close, and that's the point. Okay, so this would be the average we're shooting for, or the target value we're shooting for. Okay, then there's an upper control limit. That means, look, so long as the part averages are lower than this, I know that I can still use the part in another process and something that comes up next. Okay, I do know that if that happens, I can still use it. There's also a lower control limit down here. Okay, the lower control limit says as long as the average is bigger than this, then I know that the parts that these samples came from are acceptable and that they will still be fit for use in any subsequent process. Okay, so there's limits on these, and we're going to try to stay within the limits. Okay, and I have here, it says if the averages are between the UCL and the LCL, then the process may be in control. Notice I use the word may there because there's some times when you can be inside the limits, but you don't think your process is really in control. Okay, and we'll talk about that more in chapters 4, 5, and 6. Because we're going to talk that as process monitoring techniques. All right, so the next idea was design of experiments. We want to be able to determine the best settings for our process. Remember, we have controllable inputs. We want to see what the specifications, what these controls do, and how much variation they cause in the resulting part. Okay, because then we know which ones, if I change it just a little bit, might cause a big change in the CTQ, and the other one might have to change it a lot to have any real discernible impact on it. And you want to know that ahead of time. You can also use design of experiments to find an optimal setting or combination of the controllable inputs. So those factors that you can control, you can find the best settings for it so that you get the best part out. Okay. For the controllable factors, one may choose to use what's called a factorial design. And I'll explain what those are here in just a second. But whenever we do design of experiments, they're typically done what's considered offline. That means we're not in the middle of production. We would shut the production down, and then we would focus on a specific part of it and keep changing it until we can optimize our parameters. And we'll talk more about that later. So what is a factorial design? Suppose we have several controllable inputs, which we call factors. We want to understand how these, the influence of these inputs, one may choose to vary these factors. So we're going to have a low and high setting for each. So, for example, if we had 2 controllable factors, we could set x1, that factor, to a low value and a high value. Same thing for x2. We could set it to a low value and a high value. Okay? And that would be our experimental design is factorial. And if you notice, in this case, this is going to produce 1, 2, 3, 4 experimental units. Low, 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 high, high-low, and high-high. Then you also are going to need replication. So when you're thinking about how many objects do I need to experiment on, these can grow quite crazily big. Okay. And here, suppose we have 3 controllable factors. Well, now we add in another dimension, and you can see it's a cube, and that there are 8 experimental conditions. So if you're going to do replication, so you're going to be, if you want to be balanced design, you're going to be looking at least 16 experimental units that you're going to need to do this experiment. And if you do 3 replications, that would be 24. All right, so the other issue is acceptance sampling. So of the 3 areas. So one aspect of quality control is to ensuring that the product received or shipped meets the needed specifications. And I'll give you an idea of this. So there's outgoing. So suppose we're producing something. Okay, so we have a process that produces something. Well, before we ship it to the customer, we're going to have it go through some sort of inspection. And the goal is not to inspect every single item. The goal is to inspect only a sample of the items. Okay, that way, if the sample is good and we know we've had our process in control, that when we ship it and it arrives at the customer, we're not going to get a phone call from the customer saying, hey, why are all these parts bad? Or why did the product that you send me is wrong or defective? Because remember, they're your customer. They're the ones paying you. If you're sending them junk, they don't want to pay for junk. It also makes you look bad, and if you keep doing it, they'll look for a different vendor to buy their parts or product from. So just remember that that's important. So the next thing is well, if I'm a customer, so incoming, you can just think about now the customer is going to do an inspection. Okay, so I have a process that has been shipped to me. Let's say they're T-shirts. They've been processed and shipped to me, but before I put them to my customer, because I am the customer of the producer, but my customer, I'm going to do some sort of inspection as well to make sure if it was T-shirts that maybe if it has printing on it, it was actually printed with correct spelling. I've seen lots and lots and lots of T-shirts that have misprint spelling on them. So I would really like to make sure that my customer does not get a defective part. Or defective T-shirt. So I would check that before I put it out on the floor to my customer. Because if it is a bad shirt, then I want to send it back and get the correct item for my customer. But this is often done all through a manufacturing process. So you can think about it. If something takes multiple steps to do, one item is a customer of another item. So if we were to make coffee, think about it. There's a process that happens. I'm going to grind the coffee, right? And that's going to affect how much when I take it and brew the coffee, how I grind it is going to influence the brew of the coffee. But the process of brewing is the customer of the grind process. Okay? So if you don't grind it well enough, or you grind it too much possibly, it could cause problems. So before you would put it into the brewing, you would at least look at it and make sure it looks reasonable. But you might actually have some measurable stuff. And if it's good, you would accept it, and then you would ship it to the customer, which would be the brewer, right? So the process would be grinding. We're going to look at it. We're going to say, are there big chunks in here? Did it work? If it looks right, or I have some way to measure it, then I would actually brew it because the customer is the brewer. Otherwise, I can scrap it, so I can throw it away because maybe it's too fine and it's falling through the filter. I don't know how that would happen if he maybe had a mesh filter or something. Or you could rework it, right? Oh, these got big chunks in it, so I'm going to grind it some more. Would be a rework before you passed it on to the customer. So there are different processes. And when you scrap something out, you can many times lose all of the money that was required to bring the part to that point or the item to that point in the production process. Sometimes you can salvage some of it. For example, if it's metal, you can at least recycle the metal. But with a pizza, I don't know what you would do. you just can't rework a pizza. And, especially if you did something wrong to it, then scrapping it would mean you lost all the money on the pizza. All right, so those are the three ideas that we're going to focus on, these three different techniques, because they're each paying attention to something different. One is saying, is my process under control, so that when I know, I'm very likely to know that when I hand it to my customer is going to like it, okay? That's when you do the monitoring and you try to control the process so that it's very consistent, so your customer has a very consistent experience. And then there was the design of experiments, and that is different because you do that usually early on in the process so that you know how to control that process so that when something does happen and it goes out of control, you can bring it back into control quickly, okay? And then the other acceptance sampling is to make sure that your customer doesn't get anything bad. Okay, so there are management aspects here. So they involve the whole organization. There's what's called quality planning. That means you're going to set things up so that everybody is on board with the fact that you need to produce quality things. Whatever you're trying to produce, it needs to be quality, and you need to plan for that. Okay, you just can't assume that's going to happen. Then you're going to have quality assurance. Well, like for example, in quality planning, if I'm making coffee, the type of beans I get is quality planning, right? I'm planning to buy good beans from a good vendor so that when I use it because it's been roasted right, that's quality planning. I'm planning for things to go well. Then quality assurance is where along the way, I'm ensuring along the way that all the processes that I'm using produces a good product. And quality control and improvement is where you actually monitor it, and then you look to say, hey, is there a better way we can do this to make it even, a better way to make the part or item so that it's better overall? And these are three aspects. So there are quality philosophy and management strategies. Edward Deming was kind of like the godfather of quality control. He really put a lot of emphasis into it, and you can read about him in the book. He's quite interesting. He did a lot of stuff, and he tried to get the Americans to adopt it. They didn't particularly like it, but the Japanese loved his stuff. So here is his 14 points. So create a constancy of purpose focused on the improvement of the products and services. Okay, so make sure that the entire organization is focused on producing something good. Okay, sometimes you go to McDonald's or some other restaurant and it's absolutely clear that they don't care whether or not you get a good product or not. Okay, and that comes from the management. Okay. Adopt a new philosophy that recognizes we're in a different economic era, which means that people actually pay attention to quality. Here's an example that's quite recent. I don't know if you've heard that Starbucks got a new CEO from Chipotle. Why? Because Chipotle had an increase in sales, and Starbucks thinks it's due to something he did. My guess it's due to something that he didn't do, which is McDonald's, Wendy's, all of these other competitors raised their prices on their hamburgers and whatnot, their food product. But, quality of Chipotle is usually considered superior to just a drive-through burger, okay? It's usually considered superior, and people quit going to McDonald's to spend $10 on a meal when they could go to Chipotle to spend $8 on a burrito. They got much better quality for a lower price. So that's what I say. Adopt a new philosophy, that we're in a different economic era. It's constantly changing, and you need to adapt to it. Is what it's saying. Do not rely on mass inspection for quality control. This means I have to look at every single item that leaves. No, you want to use sampling. You want to use statistical techniques so that you don't have to spend a lot of money and time trying to control quality or to avoid a bad part leaving. You produce processes that don't produce bad parts very often. Okay? Do not award businesses to suppliers on the basis of price alone, but also consider whether they're going to give you something useful. Because you can buy something cheap and the quality might be low, and then you pass that on to your customer and they don't like it. Focus on continuous improvement. Constantly have this idea that we can do this better. We can do this better. How do we do it better? How do we do it better? And that usually is difficult for a lot of people to think about, because they're like, what's the matter with the way we do it now? Now is just fine. But remember, the economic era is constantly changing, so if you're continually improving, you don't have to worry about other competitors improving and leaving you behind. Practice modern training methods and invest on-the-job training for all employees. Okay? So make sure that as you make these changes, you actually make sure that the employees have some on-the-job training to make sure that they can implement it. Okay? Improve leadership and practice modern supervision methods, which means the supervisor should be engaged in the fact that they need to put out quality parts versus just sitting in an office someplace saying, you go and do your stuff, and they hope everything goes well. Drive out fear, because sometimes employees are afraid to say things because they're worried that they're going to get yelled at. Suppose I work at, for example, Chipotle, and I'm making some steak and I have it on the grill and everything like that, and I make the mistake of burning all of it. Okay? Well, if I'm afraid, I'll just chop it up, throw it in the bin. Everybody's going to eat it, right? Because I'm afraid to throw it away, because I'm afraid that my boss will yell at me. Okay? So if you go, oh my gosh, I made a mistake, and you knew what the mistake was and you know how to fix it, you can just say, look, I made a mistake, and you shouldn't be afraid to tell people that. The next one is break down barriers between functional areas of the business. This is really important, because a lot of groups in business don't really talk to each other, okay? The people who are in the finance don't really care what the people in shipping are doing, as long as they're shipping the stuff out. But people in finance might want to talk to the people in shipping to ensure that things go well. Everybody needs to be focused on things. Number 10, eliminate targets, slogans, and numerical goals for workforce. For example, if you on a production line, you have to produce, 100 parts per hour. Well, if you're forced to be working extremely fast, you might not do as good a job producing a quality product, where if they just had slowed it down to maybe 80 or 90, you could do a much better job with it. The next one is the same thing. Try to eliminate numerical quotas and other weird work standards. Remove barriers that discourage employees from doing their jobs. There's a lot of that goes on, like, if somebody's, let's just say, a mechanic, they might get upset that someone else did their job, even though what the person did was simple. Just keep that in mind. Institute programming education for all employees. Keep them on top of what's going on and how they can improve, because the more they know, the better the product you're going to do or you're going to make. Create a top structure and top management that will advocate for these first 13 points, because top management usually is worried about profits, quarterly profits, dividends, things like that, making sure their shareholders are happy. and they need to be advocates for these versus just get me more money. All right, so he also came up with the 7 deadly diseases of management. So lack of constancy of purpose. You're not quite sure why you're in business. Emphasis on short-term profits. Okay, if we do this, we can just get this done, and we can get short-term profits, even though in the long run we're going to make every one of our customers angry, and they will quit buying from us. But during that short term, we made a lot of money. Evaluation of performance, merit rating, and annual reviews of performance. Okay, so annual reviews. People should be reviewing what they're doing all the time, not just at the end of the year go, oh, well, you did a poor job or you did a great job. If you want to increase quality and you want to keep things improving, you want to constantly be reviewing people's performance so that they have feedback so they know how to improve it. Mobility of top management. This is a disease because if top management constantly changes, that causes a lot of problems with people who work under it. So having a consistent management is very positive. Running a company on visible figures alone. I just look at profits, or I just look at the quantity that we're turning out versus maybe some other aspects of the company that we could improve that may not translate directly into one of those figures that you look at. Excessive medical costs. If it costs a lot of money for your company to have health insurance, that's really going to cause problems. Also, excessive legal damage awards. If you're producing defective parts or products and you make a toaster and it burns people's houses down, they're going to sue you, and there's going to be class action suits. So you don't want to have that happen. So producing something quality will avoid that. I'm going to tell you that there's other standards that people look at. The ISO 9001:2000 standards. They are standards that are supposed to set up a structure of quality through reviews and stuff, and it talks about that on pages 23 to 28 in the textbook, and I'm going to tell you to read about it, and I'll probably ask you some questions about it. It's not very difficult. Just read through it and try to get a basic understanding of what they're doing. All right. Now, one of the big things in quality control is what's called a Six Sigma program, and it was developed by Motorola, okay? And this takes a little bit of calculation, and you don't really have to remember stuff from probability for this, but I'm going to use stuff from there, and hopefully it makes sense. So suppose that my process is producing products that follow a normal distribution, a nice bell shape, and we use 3 standard deviations to define our lower control limit and upper control limit. Well, just using the normal table or functions in your calculators or whatever, you'll find that to be within 3 standard deviations, the probability is 0.9973. So it's very high that one item will land in there. But we don't make just one item. Okay? Most industries are going to produce more than one item. They don't want to just sell one. Like, okay, I'm a cookie company. I made one cookie. Not one type of cookie. I made one cookie. That's not acceptable. I want to make lots of cookies, sell them so that I get lots of money. So what if we're interested in K items being acceptable? Then we need to use probability. And we're going to assume that they are independent. So let's say AI is the event that item I is acceptable and that item I and AJ are independent with a probability that's common for all I. So because if they're independent and one of them is acceptable, they're probably all likely to be acceptable in a similar way or defective in a similar way. So the probability that all items are acceptable is the intersection that every single one of them is acceptable. And if they're independent, then that means we can multiply these probabilities together, which means we end up with the probability for one item to be acceptable raised to the k power for the number of items. So here's an example. Suppose we use 3 standard deviations and we have 10 items, then the probability that all 10 are acceptable, well, we would just take 0.9973 and raise it to the 10th power, and you'll find out that it's equal to 0.9733, which is not bad. But notice this is 99% or a probability of 0.99. This is lower than that. Okay, your probability actually went down of that they're all acceptable. If I do 100 items, I would raise the 0.9973 to 100. And that will give you a probability of 0.7631. It's a lot lower. Okay, so if you look at that, it's like, wait, there's a 24% chance that at least one of them will be bad. And if we had 1,000 items, you can see it goes all the way down to 0.069. So as k increases, the likelihood that all of the items are acceptable goes down to 0. It's going towards 0. Okay. So Motorola said, well, is there a value that's high enough that it's kind of robust to what I multiply or the exponent that I use on it? Okay, so they chose 6 standard deviations. And the probability that a value lands within 6 standard deviations of the mean is this many 9s and an 8. Okay, so if we're interested in 10 items, you can see that the probability that all of them are acceptable is still really high. It's really close to 1. If I look at 100, it's still really close to 1. If I look at 1,000 items, it's still really close to 1. They are smaller, but it's going to 0 much slower. Okay, so let's suppose we're interested in being within 6 standard deviations, and we have 1,000,000 parts. Okay, we have 1,000,000 parts, then the probability that all of them are acceptable is still 0.98. So that corresponds to maybe having 2 defectives in 1,000,000, which is pretty good. Okay, so Six Sigma is trying to make the probability that you produce a defective part very small. Okay, so the goal is to set control limits, that lower control limit and the upper control limit, to 6 sigma of the specified value, the center line. This will ensure conformity among products and services, but also has another nice property. Because it's so wide, with 6 sigma, we don't need to assume the process mean and the specified center will match each other exactly. Because if I use any of these normal distributions, these pink ones, the blue one, or the other pink one, I'll get basically the same probability that I'm between -6 and 6 on a standard normal distribution. So I don't have to be perfect. Okay, that allows me to have the mean to have some variation, and it'll still work. So we can be off on the process mean by up to 1.5 standard deviations on either side of the mean, which is a really good thing because that means it's robust to the fact that, look, the mean's probably going to move around because when people make stuff, things wear down over time, or, they just aren't consistent. If I'm making coffee, that water is not exactly the consistent temperature every single time. Okay, for lots of reasons, it's not the exact same temperature, but we can be off a little bit and it'll still work. All right. There are sort of 3 phases of Six Sigma, and they call them generations. Okay, so the very first generation is let's just try to get defects eliminated. Okay, we don't want to produce defective items, things that make our customer angry and upset. Okay, we want to focus on eliminating the defects and basic variability reduction. We're trying to get whatever our product is to be as consistent as possible. That's all we're going to focus on in generation 1. Okay? Then in generation 2, we're going to still try to reduce the variability and defects, but we're going to try to tie this in a smart way. Okay? We're going to try to tie this into cost reduction. So we want to reduce our costs. So we need to choose what variables to control and what variabilities cost us money. Some variability might cost us more money than other variability. Some dimensions might really make a difference than others. And then generation 3, we're going to still do this, but we're going to work on trying to create value throughout the organization, not just on one item. All right. Individuals can be certified as Six Sigma. Well, they're called belts, like in martial arts. They have a green belt, and you would complete one project for 4 to 6 months that has an impact on a company. Okay, so it has to have an impact. A black belt typically will complete 2 projects. So you've been through this process once. A master black belt will complete 3 or more projects before they're awarded what's called a master black belt. These require an organization to help you attain these, meaning that you can't get this from a university because you need a long-term project that has an impact. And that's just not what universities do. However, the material that you're going to learn in this class correspond to being able to do this directly. You should be able to translate it directly into a black belt or green belt using the ideas at your company and demonstrate that you made an impact, and you can be awarded a green belt, a black belt, or become a master black belt. All right, so this is what we really need to focus in on is there's a problem-solving approach that Six Sigma uses, and you'll see this over and over again when people talk about Six Sigma. Most people don't think about Six Sigma as being 6 standard deviations away from the mean. They just think it's a name. But they think of more of this as being of the problem-solving approach. And it has 5 components to it. There's the define step. There's the measure step. There's the analyze step. There's the improve step. And there's the control step. Okay, and you would go through this process. Okay, especially if you're going to become attain one of those belts, you're going to go through this process and show that you can do this. And we're going to cover this in the next video extensively, what each one of these steps are. But it's known as DMAIC. And this is the problem-solving approach that Six Sigma is going to use. And if somebody asks you, do you know anything about Six Sigma? They're probably expecting you to know this versus the actual probability arguments. Other add-ons that you will often hear Six Sigma talk about is lean systems. They try to get the systems processes to be what are called lean, meaning they have the most cost reduction that they could possibly have on them. And then there's this notion of what's called Design for Six Sigma, DFSS. And there's a lot of work that goes into that because you want to not do, when you design your product, you want to design it so that Six Sigma is going to occur, okay? You want to design it so that you're producing quality products. So when you're designing the process, you want to design the process for quality versus taking a process that already exists and trying to fix it for quality so that it will have quality. So one is this design for Six Sigma is very prospective. I want to do this beforehand to ensure quality versus taking something that maybe is not producing as good of quality and try to fix it. Okay. I'm going to have you read about quality costs in the textbook. These are on pages 32 to 42. There's a bunch of stuff in there. I think you can read about it pretty easily. I'm going to focus on the items that are more direct with what we're going to keep doing throughout the semester. All right, so I'm going to end this video here. It's been almost 45 minutes, and you've listened to me this long. Congratulations. You should feel good for that you were able to endure my voice this long. All right, so I want you to have a great evening and a day, and I'll see you in the next video.